Hello everyone and welcome to today's webinar. Today's webinar is titled A New Musculoskeletal AnyBody Detailed Hand Model. My name is Christopher Iversen and I am from AnyBody Technology, and today I will be the host of this webinar. I am here together with my colleague Morten Enemark Lund.
Hi everyone.
And Morten is going to help us during the Q&A session. So today we have two external speakers, who is Lucas Engelhardt and Maximilian Melzner. Lucas is from the Scientific Computing Center of Ulm in Germany, and Maximilian is from the Laboratory for Biomechanics at OTO Regensburg, also in Germany. And together, Lucas and Maximilian have developed a new musculoskeletal hand model for the AnyBody modeling system, and they are going to give their presentation in a minute or so. But just before we start, I will give you a general introduction and overview of the AnyBody modeling system for those of you who is unfamiliar with the software or musculoskeletal modeling in general. So what is the AnyBody modeling system? The AnyBody modeling system is a software that allows you to do musculoskeletal modeling and simulations. And as input, it takes motion data as kinematics and forces, and it calculates the internal body loads as joint moments and joint reaction forces and muscle forces. And here in the bottom of the screen, you can see a screenshot from the AnyBody modeling software, which can give you an idea of how the system actually looks. At the moment, AnyBody is used in a wide variety of areas and applications. And a few examples of this is movement analysis, product optimization design, the field of sports optimization, orthopedics and rehabilitation, and assistive devices as exoskeletons. And the typical workflow in AnyBody could look something like this. So you provide the motion data as input, and then you use the body models which you or others have built, and then you provide some kind of environment, which could be an exoskeleton. Then you can use AnyBody to combine these things and run the inverse dynamics simulations. And basically then we can calculate the internal body loads as muscle forces and joint moments. We can then go on and post-process these results in some kind of finite element tool, or we can try to close the loop completely by doing some kind of design optimization and then run this loop multiple times. And I think this brings me to the end of the introduction, and I will hand over the presenter role to Maximilian instead.
So thank you, Christopher, for this kind introduction, and hello everyone. We are Lucas Engelhardt and Maximilian Melzner, and today we're going to present you our recently developed musculoskeletal hand model within the simulation software AnyBody. But before we start with our presentation, we would like to thank our financial sponsors, shown on the left and right hand side, who gave us the opportunity to realize this project. We also want to thank our heads of laboratory, Sebastian Beindorfer, Norris Simon, who were supervising the whole development of the model. The project's original starting point was a musculoskeletal PhD course organized by AnyBody Technology in 2018, on which we both took part in. So we can absolutely recommend joining such a course, both in matters of gaining knowledge and the matters of meeting people with similar research topics and fields of work, as it was in our case. Therefore, the hand model originated from a joint work between our both laboratories. The Laboratory for Biomechanics here in Regensburg, to which I, Maximilian Melzner, belongs to, and the Scientific Computing Center in Ulm, to which my colleague Lucas Engelhardt belongs to. The Laboratory for Biomechanics is located at the OTH Regensburg, and it focuses on the basic and applied research in musculoskeletal biomechanics. The Laboratory for Biomechanics in Regensburg is also an AnyBody Knowledge Center, which intensifies the cooperation and developing new human models for the research of orthopedic and ergonomic problems.
Headed through the former researcher of the Biomechanical Institute of Ulm, Dr. Uri Simon, the Scientific Computing Center has its roots in a computational biomechanical research. Beside industrial simulation projects, biomechanical research is conducted in the field of musculoskeletal simulation and fracture healing simulation. So the goal of both labs was to develop a more detailed hand model. But the first question is, why would you need a more detailed hand model at all?
So for us, the laboratory here in Regensburg is because we wanted to simulate and optimize the manual perineal protection. This is a particular kind of hand movement performed by obstetricians in order to reduce the expectant mother's damages while giving birth. Looking at the current situation, we see that about 2/3 of all babies are born naturally. But still, in up to 9% of these deliveries, mothers suffered from long-term damages. And the mentioned manual perineal protection is one way to reduce such a risk of injuries, up to 90%. But the detailed clinical description of the optimal performance is still missing. And that's a fact we wanted to change.
On the other hand, in an ongoing research project, patients who suffered the distal radius fracture are urged to perform a hand gripping exercise. Thereby, articular forces apply on the wrist joint, which foster or inhibit fracture healing. As those forces are known and an in vivo study are ethically questionable, the use of a musculoskeletal hand model in combination with such a hand gripping tool could deliver enlightenments on the occurring joint forces. For those research questions, we need a sufficient detailed hand model. But why just not use the already existing one? So let's have a look at the current hand model implemented in AnyBody. Even at a first look, you can already see that there are some drawbacks, like missing intrinsic muscles, and also the extrinsic muscles only reach up to the end of the metacarpal bones. Additionally, the degree of freedom of the abduction and adduction of the fingers is missing, and the whole wrist is simulated as just one rigid body. On the other hand, there are already some detailed models of certain parts of the human hand, like the finger models from Wu et al. And the wrist model from Eschweiler et al. But so far, there are standalone models that are not integrated into the holistic human body model. Therefore, we decided to build up a new detailed hand model from scratch. As a first step, our partners from the university in Pilsen conducted a study obtaining the necessary anatomical data. This study included a dissection of 16 cadaveric forearms and magnetic resonance imaging scans. Through this study, the patient-specific bone surface and muscle properties like physiological cross-section area, muscle length, wire, origin, insertion points, as well as the alignment of the muscles were obtained. The whole dataset, including a short description of the data obtaining procedure, is freely available. The mean values of 16 measured samples were calculated and implemented into the model. Further, the muscle alignment was obtained according to the MRI scans of one exemplary cadaveric specimen. In the following, we would like to show you what we did from the modeling approach in order to improve the existing model.
To ensure a physiological muscle popping, some obstacles like tori are implemented, which simulate annual ligaments within the finger joints and the wrist. The advantage of using tori instead of wire points is visualized on the right-hand side. As you can see, the wire points are always held on one fixed place, and hence the moment arms don't change during the flexion. Whereas for obstacles, the moment arm can be changed and adjusted. In the past, the implementation of a large number of such wrapping surfaces was always associated with a very significant increase in computation time. But due to the new wrapping algorithm integrated in the newest AnyBody release, the AnyBody version 7.3.1, the computation time could be reduced by a factor of up to 100, which makes the model much more user-friendly now. Another feature we implemented are the ligaments between the fingers, represented by the red line in the center image. This was done in order to simulate the skin's resistance during the abduction of the fingers. And those properties of the ligaments are according to the material investigations from literature. If motion data lacks on information for the distal phalangeal joint, which might be the case in actions like grasping, a finger rhythm according to the data from Van Swieten et al. Was implemented. This feature uses the strong relationship between the distal and the proximal interphalangeal joints, and thereby the angle of the distal joint is driven by the proximal joint. Another unique feature of the human hand is the origin point of the lumbricals. In contrast to regular muscles, the lumbricals do not originate from a bone, but from the tendon of the flexor digitorum profundus. Therefore, the force of the lumbricals is transmitted onto the flexor digitorum profundus tendon. Regarding the patient-specific scaling, it's also not always feasible to measure all dimensions of each finger segment. However, Buchholz et al. Proposed a linear correlation between the hand length and each finger bone. Because the study of Buchholz et al. Only included the dimension of 6 hands, we performed a study with the X-ray data of 71 patients to determine a more accurate relationship. Therefore, the length of the metacarpal, the proximal, middle, and distal phalanx can be scaled according to the hand length. According to the anthropometric data, the muscle pads are scaled as well.
However, since the model aims not to produce colorful pictures, but represents the biomechanics of the hand the best possible way, it was necessary to validate the model. This was done in 2 steps. In the first step, numerically calculated moment arms by the model and experimentally measured moment arms from literature were compared. This approach was chosen since studies indicated that the muscle line of action and moment arms are critical parameters for muscles to predict muscle and joint reaction forces. The second step was experimental validation, the decisive step that is necessary to determine whether the model prediction fits reality. This consistency between model and reality is crucial when the data obtained from the model, like in this case joint reaction forces, is to be used for answering musculoskeletal research questions. Therefore, a comparison of measured electromyographic signals of the muscles with predictive muscle activities or simulation was made. The tendon excursion method introduced by Melzner et al. Was used for the first step. This method used the length variation of the tendon, where only one axis of a joint is moved, and the articular-angular change of the joint, to calculate the moment arm of the specific muscle in respect to that chosen joint. Rehn et al. Obtained the muscle moment arm in 5 upper extremities for the extension flexion, as well as for the ulnar radial adduction of the wrist. Smuts et al. Used 7 cadaveric specimens to obtain the moment arms considering the thumb, and in the case of the index finger, Arndt et al. Conducted flexion, extension, and abduction, adduction movement of the 7 cadaveric hands. The results of Franco et al. Stated that the moment arms are nearly identical across all 4 digits for each joint. Therefore, the validation purpose, we only address the index finger. We scaled our hand model according to the measured cadaveric hands used in the experiments and performed the same movements around the joint as they did in their experimental studies, like you can see here for the flexion and abduction along the metacarpal fungular joint in the index finger. Using the elongation of the muscles, we are now able to calculate the corresponding moment arms for the muscles and compare with the data from literature. You can see here some results of this comparison. The main flexors and extensors of the wrist follow the trend of the experimental data from Rehn et al. And remains mostly within the standard deviations. Regarding the flexion extension of the metacarpal joint, the model prediction shows a comparable progression as the literature data from Arndt et al. Hereby it should be noted that the experimental data is based on only one single finger. Additionally, for the thumb, the numerically calculated moment arms of the flexion extension thumb muscle remains within the standard deviations for the literature experiments by Smuts et al. All results of this moment arm comparison, as well as more information on the development of the model, were accepted by the Journal of Computational Methods in Biomechanical and Biomedical Engineering and can soon be found under a new musculoskeletal AnyBody detailed hand model.
So let's look to the experimental validation. To provide a reference data set for the validation of the musculoskeletal hand model, an experimental study was conducted, including 5 subjects. For the measurement of the muscle activities, 4 intrinsic and 6 extrinsic muscles were considered. The electromyographic activities of these muscles were captured via surface EMG using the recommended sensor placements according to Criswell and Crum and Barbero et al. The kinematics of each hand movement were recorded with a camera-based motion capture system from Vicon. Therefore, a custom marker set of 39 markers and 22 on the hand was designed, capturing the movement of the pelvis, the thorax, humerus, forearm, and all segments of the hand. For the normalization of the EMG data, maximum voluntary contraction measurements following the recommendation from Kendall were performed. Each subject repeated the MVC measurement 3 times for each muscle group, and the maximum value was taken as normalization factor. The test subjects performed 7 different muscle-specific activation movements for the finger, thumb, and the wrist, as you can see on the right-hand side, like the abduction of the fingers, the extension of the metacarpophalangeal joint, deflection of the fingers, abduction and flexion of the thumb, and the abduction and flexion of the wrist. Each task was repeated 5 times within 1 trial, and each subject repeated every trial 3 times. To guarantee the same initial time of the EMG signals and the motion capture recordings, both measuring systems were synchronized. The validation was quantified by comparing the on and offset time points of the numerical and the measured muscle activities, which implies the time difference from which a muscle was activated or deactivated in reality and the simulation. For the respective comparison of the EMG signal and the simulated muscle activity of each task, only muscles with a measured maximum EMG activity greater than 15% in at least 50% of all performed movements were considered. Regarding the on and offsets of all tasks, muscle activities, an overall time difference of 580 milliseconds between the estimated and the measured muscle activities were computed. One of the numerical and experimental gained muscle activity can be seen on the right-hand side, where you see the muscle activity of the first dorsal interosseius during the abduction of all fingers. Nevertheless, there are some uncertainties within the comparison which have to be borne in mind. One major issue within EMG signals is crosstalk. Like neighboring muscles also produce EMG signal, which is recorded by the sensor. Particularly in the forehand, which contains 39 muscles, crosstalk is a systematic bias of the EMG signal, which is there at the EMG signal, but not in the simulation. All these results of the experimental comparison, as well as more information on the whole setup, were submitted to the Journal of Biomechanical Engineering and can hopefully soon be found under electromyography-based validation of a musculoskeletal hand model. With this validation as a background, we were now finally able to use the hand model for our actual application area, the optimization of the manual perineal protection. Therefore, obstetricians were equipped with an XSense system, the Manus VR Prime glove, as well as a specially developed force measurement glove, which detects the forces occurring on the thumb, index finger, and the middle finger. With the obtained kinematics of the obstetricians, together with the forces of the glove and the ground reaction force prediction, the forces occurring in the individual finger joints and the wrist were analyzed using the AnyBody simulation software. Preliminary results already indicate that one of the techniques used in everyday clinical practice is clearly preferable because of the lower loads within the finger and the wrist joints.
In our study, patients who suffered from distal radius fractures are urged to perform a hand gripping exercise on a daily basis. As this mechanical stimulus is the main trigger for fracture healing performance, we are now using the hand model to predict the occurring forces in the radius. The used hand gripping tool and the corresponding compression forces are modeled and the entire motion tracked by mocap analysis. At the same time, EMG measurements were taken to corroborate the calculated muscle forces. On the right, you can see the corresponding force in the wrist due to the compression of the hand gripping tool. With this, we would like to end our presentation about a recent developed hand model. We hope that we were able to give you a first insight in the hand model and that you can use it for your own purpose as well.
Yeah, thank you very much for the presentation. So just before we go to the Q&A session, I would just like to say a few words regarding our online resources. So if you want to know more about AnyBody technology, you can go and check out our website, anybodytech.com, for events and special dates, and also a full publication list of studies using the AnyBody modeling system. You can also check out anyscript.org, which is our community website for people using AnyBody. And here you can find multiple online resources as our wiki page, several blog posts and links to the repository sites. And also our forum is located on anyscript.org. And here you're able to ask questions and get help from some fellow AnyBody users. So we have a few upcoming webcasts I would like to point your attention to. On December 10th, we have a webcast titled The Effect of Hospital Bed Features and Physical Stresses on Caregivers when Repositioning Patients in Bed. And on January 12th, we have a session titled Biomechanical Investigation of a Passive Upper Extremity Exoskeleton for Manual Material Handling. It's a computational parameter study. So you can go to our website under the events section and sign up for these, or you can sign up with the email. It will be sent out shortly. And if you want to meet us, then please go ahead and send an email to sales@anybodytech.com, and we will try to set up a meeting. Or if you want to do a presentation on your own, if you already created something really cool with the AnyBody modeling system, then please feel free to send me an email at ki@anybodytech.com.